Now that we have all our results in the table here, we can move on to step number 3 in the methods. That is, we can plot a graph of absorbance on the y-axis, also known as the ordinate, versus concentration in percent volume per volume on the x-axis. Using this graph, which is known as a standard curve, we can determine the concentration of phenolphthalein in our unknown solution, that is in tubes 7 and 8. So let's have a look at how that standard curve may look. And Bob has already drawn up a standard curve for us. So let's dissect this a little bit further. So on this axis here, we have absorbance.
Which is also known as our y-axis.
Yes. And absorbance, remember, we measured using a wavelength of 550 nanometers.
Yep.
All right, down here on our x-axis, we have the concentration of phenolphthalein. And note, even though that we're using percent volume per volume, the real concentration of phenolphthalein used was in fact 4 millimolar. But we don't normally use this concentration, these units in this Prac, because normally the Prac is delivered before students are exposed to the concept of the mole and molarity. Okay?
Hence, to simplify, we use the whole concept of percentage.
That's right.
To start off with.
All right, now let's look at what Bob's done here. He has taken the first result,
which would be, say, test tube number 2. Test tube number 1, and that will give us an absorbance reading of 0, which is actually on the origin, right, at this point here. Test tube number 2 has an absorbance reading of 0.019 at a final concentration, in this case of 0.8% phenolphthalein. So let's do that. So we've gone up to an absorbance reading of 0.019, which is, now remember, this is just a rough graph. So this is an absorbance reading of 0.019 at a final concentration of 0.8% phenolphthalein, which is approximately there. So what we do is we move across, up, and that's where our point, or that's where we plot that particular point or dot. Test tube number 3, in this case, has an absorbance reading of 0.61 at a final concentration of 1.6. Therefore, we move up from 1.6 here, an absorbance reading of 0.61, and that's where we plot that point there. Test tube number 4 has an absorbance reading of 0.85 at a final concentration of 2.4, and that's where this point is located. Test tube number 5 has an absorbance reading of 0.118, which is just approximately there, and a final concentration of 3.2. So what we do is we move across, up, and that's where that point is located. And the final test tube is test tube number 6, which has an absorbance reading of 0.141 at a final concentration of 4. So we go 4, 0.141, which is approximately there, and that's where this point is now located. After we've plotted all those points, we then put what is known as a line of best fit. And in this case, the line of best fit will actually go through the origin, 0, and does not necessarily have to go through every point. What it's shown is a rough estimate of, if this experiment was done, numerous times, okay, and you took the average, most of those points would actually line up on that line of best fit, on that line which is also known as the line of best fit. But due to Bob's technique or other variables, these points don't actually line up perfectly on that line of best fit, which is what you'd expect in a real world situation.
Not too bad, Bob.
Thank you.
And Bob, can you actually extend, if for example the concentration of the unknown was up here somewhere, could you just extend this line of best fit?
In this experiment, no. But what you could do in order to bring those absorbance values in range of this line of best fit, what you could do is actually dilute your unknown concentration. For example, you may do a 1 in 2 dilution or 1 in 10 dilution, and therefore bring those absorbance value within that range of the line of best fit. Now, it's important to note you don't over dilute your unknown, therefore bring it right down here, because this is where your most not as accurate results are located. For example, see how this point here is not as close to line as, for example, test tube number 3, 4 or 5 or 6. So you don't want to over dilute your unknown solution.
That's great, Bob. And so this is just a rough example of a standard curve. How could students actually do this in a more accurate way?
They could graph this manually by drawing on a bit of graph paper, or use Excel spreadsheet. Now, a lot of students struggle with the whole understanding of what goes on your y-axis, which is your vertical, compared to your horizontal. And the way I like to think of it is the thing that I physically can control, which in this case is the concentration of phenolphthalein. I'm the one that physically pipettes that concentration or that volume in a particular test tube. So therefore, that goes on the x-axis, which is the thing that I can control, or the demonstrator or the person performing the experiment can control. And your absorbance values are always relative to your x-axis. So, sorry, your y-axis is always relative to your x-axis. So in this case, your absorbance, which is determined by your phenolphthalein concentration, will be located in the y-axis.
That's terrific. Thank you, Bob.
You're welcome, Barry.